In mathematics, the Hermite polynomials are a classical orthogonal polynomial sequence that arise in probability, such as the Edgeworth series. In combinatorics, as an example of an Appell sequence, obeying the umbral calculus. In numerical analysis as Gaussian quadrature. In finite element methods as shape functions for beams. And in physics, where they give rise to the eigenstates of the quantum harmonic oscillator. They are also used in systems theory in connection with nonlinear operations on Gaussian noise. They were defined by Laplace though in scarcely recognizable form, and studied in detail by Chebyshev. Chebyshev's work was overlooked and they were named later after Charles Hermite, who wrote on the polynomials in 1864 describing them as new. They were consequently not new, although in later 1865 papers Hermite was the first to define the multidimensional polynomials. Definition: there are two different ways of standardizing the Hermite polynomials. The probabilists' Hermite polynomials are given by, while the physicists' Hermite polynomials are given by. These two definitions are not exactly identical. Each one is a rescaling of the other. These are Hermite polynomial sequences of different variances. See the material on variances below. The notation he and H is that used in the standard references Tom H. Cowanwinder, Roderick S. C. Wong, and Rilov Kokuk A. Aller, 2010, and Abramowitz and Stegun. The polynomials Hen are sometimes denoted by Hn, especially in probability theory, because is the probability density function for the normal distribution with expected value 0 and standard deviation 1. The first 11 probabilists' Hermite polynomials are, and the first 11 physicists' Hermite polynomials are. Properties: Hn is a polynomial of degree n. The probabilists' version he is leading coefficient 1, while the physicists' version H is leading coefficient 2n. Orthogonality: Hn, x, and hen, x, are nth degree polynomials for now equals 0, 1, 2, 3, These polynomials are orthogonal with respect to the weight function, AAAA, or AAAA, that is, we have. Furthermore, AAA, or AAAA. The probabilist polynomials are thus orthogonal with respect to the standard normal probability density function. Completeness: the Hermite polynomials form an orthogonal basis of the Hilbert space of functions satisfying, in which the inner product is given by the integral including the Gaussian weight function w, x, defined in the preceding section. An orthogonal basis for L2, R, AW, x, ADX, is a complete orthogonal system. For an orthogonal system, completeness is equivalent to the fact that the zero function is the only function L2, R, AW, x, ADX, orthogonal to all functions in the system. Since the linear span of Hermite polynomials is the space of all polynomials, one has to show that if A satisfies for every na per beta 0, then phi equals A0. One possible way to do this is to appreciate that the entire function vanishes identically. The fact then that f, it, equals A0 for every t real means that the Fourier transform of f, x, aexp, ax2, is 0, hence f is 0 almost everywhere. Variants of the above completeness proof apply to other weights with exponential decay. In the Hermite case, it is also possible to prove an explicit identity that implies completeness. An equivalent formulation of the fact that Hermite polynomials are an orthogonal basis for L2, R, AW, x, ADX, consists in introducing Hermite functions, and in saying that the Hermite functions are an orthonormal basis for L2, R. Hermite's differential equation: the probabilists' Hermite polynomials are solutions of the differential equation, where I is a constant, with the boundary conditions that U should be polynomially bounded at infinity. With these boundary conditions, the equation has solutions only if I is a non-negative integer, and up to an overall scaling, the solution is uniquely given by U, x, A equals A, x. Rewriting the differential equation as an eigenvalue problem. Solutions are the eigenfunctions of the differential operator L. This eigenvalue problem is called the Hermite equation, although the term is also used for the closely related equation, whose solutions are the physicist's Hermite polynomials. With more general boundary conditions, the Hermite polynomials can be generalized to obtain more general analytic functions A, Z, for Ia complex index. An explicit formula can be given in terms of a contour integral. Recursion relation: the sequence of Hermite polynomials also satisfies the recursion, A. Individual coefficients are related by the following recursion formula. And A, 0, 0, equals 1, A, 1, 0, equals 0, A, 1, 1, equals 1. Assuming A, physicists, individual coefficients are related by the following recursion formula. And A, 0, 0, equals 1, A, 1, 0, equals 0, A, 1, 1, equals 2. The Hermite polynomials constitute an Appell sequence, that is, they are a polynomial sequence satisfying the identity, AA, or, equivalently, by Taylor expanding, AA, in consequence, for the mth derivatives the following relations hold, AA, it follows that the Hermite polynomials also satisfy the recurrence relation, AA, These last relations, together with the initial polynomials HO, x, and H1, x, can be used in practice to compute the polynomials quickly. Chura-N's inequalities are. Moreover, the following multiplication theorem holds. Explicit expression: the physicist's Hermite polynomials can be written explicitly as for even value of n and for odd values of n. These two equations may be combined into one using the floor function. The probabilist's Hermite polynomials have similar formulas, which may be obtained from these by replacing the power of 2x with the corresponding power u, and multiplying the entire sum by 2an/2. Generating function: the Hermite polynomials are given by the exponential generating function, AA. This equality is valid for all x, T complex, and can be obtained by writing the Taylor expansion at x of the entire functions REXP, AZ2. One can also derive the generating function by using Cauchy's integral formula to write the Hermite polynomials as. Using this in the sum, one can evaluate the remaining integral using the calculus of residues and arrive at the desired generating function. Expected values: if x is a random variable with a normal distribution with standard deviation 1 and expected value I1/4, then, the moments of the standard normal may be read off directly from the relation for even indices. Where is the double factorial? Note that the above expression is a special case of a representation of the probabilist's Hermite polynomials as moments. Asymptotic expansion: asymptotically, as NAA, the expansion, AA, physicist, holds true. For certain cases concerning a wider range of evaluation, it is necessary to include a factor for changing amplitude, which, using Stirling's approximation, can be further simplified, in the limit, 2. This expansion is needed to resolve the wave function of a quantum harmonic oscillator such that it agrees with the classical approximation in the limit of the correspondence principle. A finer approximation, which takes into account the uneven spacing of the zeros near the edges, makes use of the substitution, with which one has the uniform approximation. Similar approximations hold for the monotonic and transition regions. Specifically, if, then, while for, with T complex and bounded, then, where I, A, is the Airy function of the first kind. Special values: the Hermite polynomials evaluated at zero argument are called Hermite numbers, which satisfy the recursion relation. In terms of the probabilist's polynomials, this translates to relations to other functions. Laguerre polynomials: the Hermite polynomials can be expressed as a special case of the Laguerre polynomials. Relation to confluent hypergeometric functions: the Hermite polynomials can be expressed as a special case of the parabolic cylinder functions. where is Whittaker's confluent hypergeometric function? Similarly, AA, where is Kummer's confluent hypergeometric function? Differential operator representation, the probabilist's Hermite polynomials satisfy the identity where D represents differentiation with respect to x, and the exponential is interpreted by expanding it as a power series. There are no delicate questions of convergence of the series when it operates on polynomials, since all but finitely many terms vanish. Since the power series coefficients of the exponential are well known, and higher-order derivatives of the monomial xn can be written down explicitly, this differential operator representation gives rise to a concrete formula for the coefficients of Hn that can be used to quickly compute these polynomials. Since the formal expression for the Weierstrass transform W is E2, we see that the Weierstrass transform OFN hen, xh2, is xn. Essentially, the Weierstrass transform thus turns a series of Hermite polynomials into a corresponding Maclaurin series. The existence of some formal power series G, D, with non-zero constant coefficient, such that hen, x, equals G, D, xn, is another equivalent to the statement that these polynomials form an Appell sequence as CFW. Since they are an Appell sequence, they are a Forty or a Scheffer sequence. Contour integral representation, from the generating function representation above, we see that the Hermite polynomials have a representation in terms of a contour integral, as AA, with the contour encircling the origin. Generalizations: the Hermite polynomials defined above are orthogonal with respect to the standard normal probability distribution, whose density function is, which has expected value 0 and variance 1. Scaling: one may analogously speak of generalized Hermite polynomials of variance I plus or minus, where I plus or minus is any positive number. These are then orthogonal with respect to the normal probability distribution whose density function is. They are given by. In particular, the physicist's Hermite polynomials are thus. Now, if then the polynomial sequence whose nth term is called the umbral composition of the two polynomial sequences. It can be shown to satisfy the identities, and the last identity is expressed by saying that this parameterized family of polynomial sequences is a cross-sequence. Negative variance: since polynomial sequences form a group under the operation of umbral composition, one may denote by the sequence that is inverse to the one similarly denoted but without the minus sign, and thus speak of Hermite polynomials of negative variance. For I plus or minus 0, the coefficients of hen, ai plus or minus, x, are just the absolute values of the corresponding coefficients of hen, I plus or minus, x. These arise as moments of normal probability distributions, the nth moment of the normal distribution with expected value I1/4 and variance I2 florenses, where x is a random variable with a specified normal distribution. A special case of the cross-sequence identity then says that applications, Hermite functions, one can define the Hermite functions from the physicist's polynomials. Since these functions contain the square root of the weight function, and have been scaled appropriately, they are orthonormal and form an orthonormal basis of L2, R. This fact is equivalent to the corresponding statement for Hermite polynomials. The Hermite functions are closely related to the Whittaker function Dn, Z, and thereby to other parabolic cylinder functions. The Hermite functions satisfy the differential equation. This equation is equivalent to the Schur-Paragraph-Dingo equation for a harmonic oscillator in quantum mechanics, so these functions are the eigenfunctions. Recursion relation: following recursion relations of Hermite polynomials, the Hermite functions obey, as well as extending the first relation to the arbitrary mth derivatives for any positive integer m leads to. This formula can be used in connection with the recurrence relations for hen and in to calculate any derivative of the Hermite functions efficiently. Kramer-Copyright-R's inequality: the Hermite functions satisfy the following bound due to Harold Kramer-Copyright-R. For x real, where the constant k is less than 1.086435. Hermite functions as eigenfunctions of the Fourier transform. The Hermite functions in x are a set of eigenfunctions of the continuous Fourier transform. To see this, take the physicist's version of the generating function and multiply by exp, ax2/2. This gives. Choosing the unitary representation of the Fourier transform, the Fourier transform of the left-hand side is given by. The Fourier transform of the right-hand side is given by. Equating like powers of t in the transformed versions of the left and right-hand sides finally yields. The Hermite functions in x are thus an orthonormal basis of L2, which diagonalizes the Fourier transform operator. In this case, we chose the unitary version of the Fourier transform, so the eigenvalues are n. The ensuing resolution of the identity then serves to define powers, including fractional ones, of the Fourier transform, to wit a fractional Fourier transform generalization, in effect a Euler kernel. Wiener distributions of Hermite functions. The Wiener distribution function of the nth order Hermite function is related to the nth order Laguerre polynomial. The Laguerre polynomials are leading to the oscillator Laguerre functions. For all natural integers n, it is straightforward to see that where the Wiener distribution of a function x or L2, a is defined as. This is a fundamental result for the quantum harmonic oscillator discovered by Hip Grunwald in 1946 in his PhD thesis. It is the standard paradigm of quantum mechanics in phase space. There are further relations between the two families of polynomials. Combinatorial interpretation of coefficients. In the Hermite polynomial hen, x, of variance 1, the absolute value of the coefficient of xk is the number of partitions of an n-member set into k singletons m/2 pairs. The sum of the absolute values of the coefficients gives the total number of partitions into singletons and pairs, the so-called telephone numbers, 1, 1, 2, 4, 10, 26, 76, 232, 764, 2620, 9496. These numbers may also be expressed as a special value of the Hermite polynomials. Completeness relation. The Christoffler-Darboux formula for Hermite polynomials reads. Moreover, the following completeness identity for the above Hermite functions holds in the sense of distributions. Whereas the Dirac delta function, in the Hermite functions, and I, ZAAY, represents the Liebsche measure on the line y equals ax in a 2, normalized so that its projection on the horizontal axis is the usual Liebsche measure. This distributional identity follows by taking way AA1 in Euler's formula, valid when a 1 AA way a 1, which is often stated equivalently as a separable kernel. The function OE, x, a y, AU, is the bivariate Gaussian probability density on a 2 which is, when U is close to 1, very concentrated around the line y equals x, and very spread out on that line. It follows that when f, g are continuous and compactly supported, this yields that f can be expressed in Hermite functions, as the sum of a series of vectors in L2, namely. In order to prove the above equality for E, x, a y, a u, the Fourier transform of Gaussian functions is used repeatedly. The Hermite polynomial is then represented as. With this representation for Hn, x, and Hn, y, it is evident that. And this yields the desired resolution of the identity result, using again the Fourier transform of Gaussian kernels under the substitution. See also, Euler kernel, Tura-Enz inequalities, parabolic cylinder function, notes. References, Abramowitz, Milton. Stegun, Irene A., eds., Chapter 22, Handbook of Mathematical Functions with Formulas, Graphs, and Mathematical Tables, New York, Dover, PA 773, ISBN A978-0486612720, MRO 167642A. Caron, Richard. Hilbert, David, Methods of Mathematical Physics, Volume I, Wiley InterScience C, Erda Copyright Lie, Arthur. Magnus, Wilhelm. Oberhettinger, Fritz. Tricormi, Francesco G., Higher Transcendental Functions. Vol. 2, McGraw-Hiller, Fedoriuk, M.V., Hermite Functions, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Cohenwinder, Tom H. Wong, Roderick S.C. Kokuk, Rylov. Swartau, Rena. Copyright F, Orthogonal Polynomials, Inulva, Frank W.J. Lozier, Daniel M. Berweisvert, Ronald F. Clark, Charles W., NIST Handbook of Mathematical Functions, Cambridge University Press, ISBN A978-0521192255, MRA 2723248. Schuart, Hill, Walsh, Bibliography on Hermite Polynomials, 1940, Laplace, P.S., Mar. Copyright M. C.L. Sci. Math. Phys. Inst. France 58, 279 € 347 a, Suetin, P.K., HH 047010, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Siger, Garbon, Orthogonal Polynomials, American Mathematical Society, Wiener, Norbert, The Fourier Integral and Certain of Its Applications, New York, Dover Publications, ISBN A0-486-60272-9, Whittaker, E.T. Watson, G.N., 4th, ed., A Course of Modern Analysis, London, Cambridge University Press. Tem, Nico, Special Functions, An Introduction to the Classical Functions of Mathematical Physics, Wiley, New York, 1996, external links, Weierstein, Eric W., Hermite Polynomial, MathWorld. Module for Hermite Polynomial Interpolation by John H. Matthews.